Okay, so this is going to have a lot of algebra, but I'll just go very fast through the algebra. Don't get frightened or bored or lost with the algebra. We're going to hit a point in the end where there is something really cool and interpretable. Yeah, and that's about estimating parameters. So you give me data, and this data is drawn from some underlying data generating mechanism, yeah, through a model. And that model has parameters in it. And my job is to estimate, given the probabilistic model of that generating process, estimate those parameters. This is what I'm after. So we have data. Okay, let's start with that. We have data and we have a model. And that model could be the data came from a Gaussian density. Okay. We have parameters relating to this model. And one of those could be the mean of that Gaussian. Yeah, so we all know about Gaussians, so it has a mean and standard deviation, and this could be a parameter. And you give me a bunch of this data and say, estimate the parameters of given that data, okay? And there are two ways of thinking about this. One is known as the frequentist thought, and if I go wrong here, Stephen is supposed to correct me, yes. What we think here is that the data that you have given me is just one realization from that underlying process. That underlying process is Gaussian. You pull out 100 numbers and give me that. Yeah. Next time I come and do this experiment, you might pull another different numbers, 100 numbers. But both came from that distribution, and you ask me what the mean of that is. Yeah. So repeated experiments will give slightly different estimates. So if I estimate the mean from 100 numbers you give me, I will get a value for that mean. Next time I come and do the thing, you give me another 100 numbers. I calculate the mean from those 100 numbers. It could be slightly different. Yeah. Another 100 numbers, it could be slightly different. Yeah. There will be a variation in that. Yeah. And that's the quality of that estimate that I'm making. If I did this with repetitions of 1,000 numbers, then that variation I get would be very small. Yeah, so that's intuitive, but that's what's underlying the idea of frequentist thought. Okay? If that's exactly what I said just now. If the experiment uses a lot of data, that variation could be small. And what we do is we define this probabilistic model that we know of, which is the Gaussian, of which I'm going to calculate the mean, and we maximize the likelihood. We are asking the question, what should the mean be so that the chance of realizing the observations that we are making is maximum. Okay. And in doing that, we got to be careful about these two terms, and I'll come back to that in a little bit more formal setting of bias and variance. The particular way in which I approach calculating that mean, yeah, if I'm not careful, could have a bias. That is, every time I do this, it'll give me a slightly different answer, but the average of those answers will not be the correct one. Okay. Variance is every time I do this, I have a slightly different value. And how different that is the variance in what we do. The other completely different way of looking at this is the Bayesian thought. So the Bayesian thought doesn't say you repeat these experiments. You say we are interested in characterizing this parameter and an uncertainty on that. There we might start with some prior knowledge. And that prior knowledge might say the mean is not 24, the mean could be 25. Based on some external information that I have gathered about the mean. And then I might say I have some uncertainty on that. I could say it's 25 plus or minus 5. Yeah. And then the data that you give me has some information on it. And I'm going to combine the likelihood that comes from the data that you gave me and the prior knowledge with which I started working on the problems to get a posterior uncertainty on that mean. Okay, so is that storyline clear? Let's just repeat this. There is, think about, I don't know, if I set an exam, the average grade you guys would get, okay? So just to be nice, maybe it's 80, okay? So 80 marks you will all get is my prior knowledge, yeah? But there will also be a distribution around that, yeah? So if I set an exam paper and draw about 10 of you and take those numbers, it could be, I don't know, 75, 78, 82, 83, and so on. I calculate the average and I report to the boss, the average of this class is 80. Yeah. So, but if I did it again or with another sample on that corner, then I might not get 80, I might get 81. On that corner, I might get 82. Yeah, these are different. But if I average the 78, the 81, and the 83, I might get 80. Yeah, so that's how the frequentist idea works. How does the Bayesian idea work? I might come in, having taught in some other university, yeah, where the students are not particularly bright as you guys. Yeah, I might come in and say, bro, machine learning course average is going to be 60. Yeah, and based on my experience there, I might say it's somewhere between 65 and 70. So, no, sorry, 60, 55 and 65. So I have an uncertainty with which I'm coming here. And then I come and look at your exam grades. They're all very high. Yeah. So the Bayesian school of thought is about finding a balance between what the prior I came into the room with and what I see in data. Yeah. It may well be I'm very, very strong-minded, and with my 60, my uncertainty of the initial 60 could be just 1. I'm going to say it's 60 plus or minus 1. So it's 59 to 61. Yeah, so that's a very strong prior with which I've come to this university. So then I have to see a lot of your data before I will change my mind. Yeah, so that's the kind of discussion one has to have in balancing out the likelihood you see from the data and the prior with which you started setting up the problem, and to combine them to come up with a posterior. Okay, yeah.
So if the prior is reasonable, then if you have enough data, the bound to end up with a suitable.
So the question is, if the prior is reasonable, if you have enough data, we are bound to come with a correct answer, or a so the prior has to be reasonable from the knowledge of the problem domain. That's correct. So as soon as I got appointed here, I should have had a conversation with people running the teaching program and said, I'm not going to use 60 as a number, and that's not very nice. And the guys here might have told me 75 is reasonable because they have tested your chemistry, physics, applied maths, and so on. Therefore, in machine learning, they might not score that low. Yeah, so I would have modified my prior there. And if that prior is close to the ground truth, or then it may well be, I will get a good estimate from a very small number of samples. Yeah, and I don't need a lot of samples before I change my prior. Yeah. Good. So that's what these two are. Okay, so let's go into likelihood and log likelihood and that sort of stuff. So there is some unknown parameter omega j, and what am I doing here? Okay. So I've gone into multivariate Gaussian here, so I need to pause a little bit here, and I'm going to write something on the board. So, okay, so now this would, again, something that would make half of you bored, but I need to get there. So you know about Gaussian distribution of one variable. So if I wrote so everyone knows this, right? Yeah. And this is something, the shape of which kind of looks like that. And there is a mean, and this width has something to do with the standard deviation. This everyone knows, yeah? But that's univariate. And one dimension is boring. There's not much happening in one dimension. We want to work with multi-dimensions. So then what we need is the probability density over a vector. Yeah. So then that was going to be d by 2, where x is d dimensions, some matrix determinant to the half, so that's a multivariate version of this. Oops, I should not move this up. Is this coming across as readable, Sunny, on the, you can, okay, okay. So guys who are on Zoom, if what I write cannot be read, just shout, protest. Okay, so now so this one has, the mean is a vector here. and this is a covariance matrix. Okay. And there are a couple of things you should know about this. Jumping from one dimensions to multiple dimensions is a little bit complicated. So in one dimension, I can draw this sketch quite nicely and very fast. When I go to multi-dimensions, I have a couple of different possibilities. So let's say these two. Yeah, in 2 dimensions, I could think of something like that. So my vector x consists of x1, x2, x1, x2. And what would the distribution of points data drawn from this density look like in this space? That's the question, right? So it could be, it's going to be scattered in different places. So for this one, data from this density would look like this. Lots of the time, we will have data very close to the mean. Once in a while, you get data far away from that. Yeah? Some 95% of the time, you're within 1 standard deviation either side or something like that. Yeah, you know, this sort of thing. But when you go here, you have it doesn't immediately map to that. Depending on what this covariance matrix is, yeah. So the simplest distribution of data would be kind of symmetrical like this, right? Isotropic. Yeah. Or it could be a little bit more complicated. You might have data that looks like this. Yeah. And this would be, what I've written here, is a function of a vector in which the mean and the covariance matrix are parameters. And if I draw equal height contours on this function, after fitting it to this kind of data, in this case, I will have circles like that. Yeah. In this case, I will have ellipses like that. Yeah. And what determines the shape of this is the C matrix. Yeah. A third one, just to be complete, is the distribution being axis aligned. That is also possible. Yeah. So what are things you could say about this? In this one, you might say x1 and x2 are, complete the sentence, one of you. In this case, these two variables I have do not have something. Correlation, yes, they're not correlated, yeah? So here is positively correlated. You can, of course, have the reverse of that over that way, negatively correlated. What that means is that over here, if you tell me something about x1, you're not telling me anything about x2. In this one, if you tell me x1 is high, yeah, then you're also hinting to me that x2 is also likely to be high. Yeah, so if you pluck one of these people here, then x1 is high, then x2 is likely to be high. Okay. Over here, they are uncorrelated, but just that x1 has a larger spread than x2. Yeah, those are very basic things that come out of multivariate Gaussian, and you will perhaps all of you know that that's matrix inverse, that's a determinant to the half. Okay. Oh, maybe I should say this also here. There's something very fundamental about this that would be extremely useful. Yeah, and that's the following. I would write this density by using this notation, a curly n, m, c. Okay. Something very fundamental about this, if you give me a variable x, which is distributed by a normal density with mean m and covariance matrix C, yeah. Now, if you subject this to a linear transformation, Yeah, a linear transform is multiply by something and add something to it. Forget the adding part now, just multiply by something. So I can construct a vector y by multiplying x by a. Yeah, so I have a matrix here, I have a vector here, this product gives me another vector. Yeah. This y also has a Gaussian density, and I can immediately write down the mean and covariance matrix of that. Okay. So the mean is going to be at A times M, and the covariance matrix would be A times C times A transpose. Okay, that's a property that immediately follows. And this is extremely useful, and we'll see that in a minute. Yeah. So what you have here is that if you have a multivariate vector variable whose distribution is multivariate normal or multivariate Gaussian, then a linear transform of that will also have a multivariate Gaussian distribution whose mean and covariance matrix can be immediately written down in closed form. Okay, so that's something all of you should be able to articulate, to be able to say it. Yeah. So pretend you're traveling by train and you're sitting in one of these 4 people sitting table thing, and you are revising for your machine learning exam. And this is for the men in the room. There's a lady of significant appeal looking across you, say, and she asks you, what are you doing? And you might say that, well, I'm saying that if there is a vector variable that's distributed according to multivariate Gaussian, and if I subject this to a linear transform, then the resulting vector variable is also multivariate Gaussian, and the mean and covariance I can write down immediately. Yeah, and this would be of this could impress this person on the other side. You know, you don't think so? I know this for sure. I can tell you, I married her. Okay, so that's where are we going to go with this? That's my next question. There are 2 things I can do using this property. This property is extremely important. I just wanted to wake you guys up by telling that story, okay? This is extremely important. So what are things I can do with it? If you tell me, okay, look at the univariate case. Look at the univariate case, and you tell me there is a mean at some 2.5 and a variance that is 1.0. And you tell me, bring me 100 numbers that will have a mean of 2.5 and a variance of 1.0. Yeah, how would I do this? Yeah, I want to generate random numbers that are of a particular distribution, which have a particular value for the parameters. And the idea there is known as sampling. Sampling from a given probability density. There's huge literature on this. Okay. If the distribution is uniform between 0 and 1, if you tell me, give me 100 numbers that are uniformly distributed between 0 and 1, what would I do? Yeah, I would go and open my Python program. Yeah, and I would say I would call NumPy or something, and I would say np.random.rand 100 by 1, and that will use a pseudo-random number generator to give you 100 uniformly distributed random numbers. Yeah, this much you know. There's nothing called perfectly random, but there's a pseudo-random number generator that will give you that. That pseudo-random number generator will also be somewhat periodic, but over a very, very long period of time, and we are not going to be here long enough to see that. Okay, so for us, for our practical purposes, that's going to give us random numbers. If you ask me for Gaussian random numbers, again, there is an inbuilt thing, random normal, 100 by 1, will give you Gaussian random numbers with 0 mean and unit variance. What I want is 2.5 mean and unit variance. How would I do that? Linear transform. I would generate these 100 and add 2.5 to each of them. Yeah, then the distribution I have generated shift this way, and I have 100 random numbers, mean is 2.5. If instead of variance 1, you ask me for variance 4, yeah, then what would I do? I would generate the 100 random numbers this way, multiply every one by 2, yeah, then the variance will become 4. Yeah, so there are little tricks I can do to use a facility that my computer provides to draw random numbers according to some other distribution. And the property I'm using is that linear transforms of Gaussian random numbers would also give me Gaussian random numbers. Yeah, that works here as well. Okay, so sampling from a Gaussian distribution, a multivariate Gaussian distribution, is one thing we can do because of this property that we were revising in the train. Yeah, there is another one we can do. That's another cool thing we can do. What we can ask for is, suppose you give me data according to that distribution. And then you go and think of a direction here, U. And you ask me, what happens if I were to project all this data onto this direction? Yeah, you may be very curious. You might just ask me, hey, there's a direction U, and I want to take each of these data and project. You understand what I mean by projection? From each of these lines, points, I'm going to draw perpendiculars to these guys. Yeah, and if I did that, then I will have lots of blue points here, 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 and close to this mean there will be lots of them. Over there, there will be a few of them. Yeah. So now you may want to try and understand what this distribution looks like. Yeah. In this picture, that's 2 dimensions. The red ones are 2 dimensions. The projected ones are 1 dimension. Yeah. I can use this property. Yeah. I can use this. How can I use this? This A times X to me is simply U transpose X. Yeah, I have a direction U. So when I say direction, you should immediately know that I've normalized U. U has a unit magnitude. Yeah, so these projections, where they are, I can get by U transpose X. Yeah, so every red cross is an X. Yeah, U transpose X is the projection along this. And then I go and look at this. Where is the mean? The mean is going to be at U transpose X. Yeah. What's the variance of this? In place of A, I'm going to write U transpose. So I'm going to have U transpose C U. Yeah. And that's the variance of the projections along a direction you give me. Yeah, sorry. Okay, we need to finish for coffee. So do you want 1 minute or coffee? 1 minute, 1 minute, okay. So 2, okay. So what I have shown you is that this stuff that you were revising in the train, that linear transforms of a multivariate Gaussian, is also going to give me multivariate Gaussian. Yeah. And in the case of the transform giving me univariate, then it's not multivariate, it's multivariate with 1. Okay. And I can figure out where the mean will project. Yeah, I can figure out what's the spread along this is. The idea of variance is spread. Variance tells you how spread out data is. Okay, so if you now go and look at lab sheet 1. Okay, so I'm, in this one, I'm taking students through, because similar to you guys, it's a very variety of background students I teach, and I have to bring them to the same speed. So I take them through various little things in linear algebra. So what are determinants? What are quadratic forms? How do you calculate angles between 2 vectors, and blah, blah, blah. And leading up to this important concept called singular value decomposition. Yeah, this is, you know, this is like oxygen for many of us. Yeah, it's a driver of so many different things that we can try to understand what's going on, and a thing underlying the derivation of various different algebras. So that's kind of the advanced topic to which one should reach to get deep into machine learning. Okay. So there are bits of Python code through which you are taken there, and this tells you of some really nice resources. There's a thing called the Matrix Cookbook. It's out there as PDF. You can find it with Google within a second. And this should be something, it's like bedside stuff, right? You keep it next to your bed always. To understand singular value decomposition, I might say a bit more about that later. In YouTube, there's a video called SPD Song. So listen to it, it's great fun. It's a beautiful job they've done. But to get into linear algebra seriously, Gilbert Strang is the master of the subject. He has written textbooks on this. His textbooks and YouTube videos are absolutely stunning. Okay. And then we can talk about random numbers with univariate densities, drawing histograms of stuff. And there is an important thing that comes from what's known as the central limit theorem. So remember, we talked about uniform densities. We talked about Gaussian densities. If you generate uniform random numbers and keep adding them, then asymptotically it becomes Gaussian. Yeah, and there's a small exercise to understand that. Then we're going to bivariate. So multivariate in 2 dimensions is bivariate. And this one lets you do 2 things. One is how to sample from a given density. How do you generate 100 samples or 1,000 samples? And the other is if you are given data from that density, how do you project it onto a given direction? And the most important thing you'll learn towards the end of this exercise, if you go through that, is depending on which direction you are looking, the variance of the projected data changes. There is a certain direction you can look when the projected variance is maximum. Yeah. And after coffee, I'll tell you about this. Okay. Okay, so let's get back to where we were. And there were a couple of questions, and based on that, because machine learning has various communities coming in, sometimes notations can also be painful. So for statisticians, covariates are X goes in, response variables are Y that comes out, the unknown parameters are betas. Yeah. For some machine learning people, because the response is a target, it's a T, and the inputs become X, continues to be X. The unknowns are thetas, because they're parameters. To me, parameters have to be theta. Yeah. It gets even worse, because if you have, to me, X is a scalar, and I write X with a line to make it a vector. Yeah. And a matrix is uppercase. This is what I use. When I LaTeX things, I don't use underscore, I put a bold X. So bold is vector. So that's very consistent. And there are crazy people in physics departments for whom X vector is that. You know, how can this be? Okay, so, but you just have to learn to live with that world. There's nothing you can do. It's confusing, but there's no consistency there. Okay, so so a couple of points from here. So suppose I had Gaussian density, univariate, and you give me 100 numbers, xn, n going from 1, blah, blah, to, let's say n numbers. That's much nicer. Yeah. And you know this from primary school. If you ask me what the estimate of the mean is, then what do? You add them up, xn, and divide by how many n's were there, right? Yeah, this we know. We punch these numbers and do that. If you ask me what the standard deviation is, or let's say variance is, then what do? You take each of the data, and then you subtract from that the mean you have already calculated, you square it, you sum it over all of them, and do that. Yeah? And standard deviation is the square root of that. And then you also know that there is a sigma n and sigma n minus 1 in your pocket calculator. Yeah. And it's homework for you to figure out what that is. Okay. I'm not going to tell you. Okay. In the multivariate case, where I have m and c as parameters, then it's exactly the same. So your estimate of the mean is that, yeah? And your estimate of the covariance matrix is transpose. Yeah. And again, I have a kind of consistency in my life, and many people who are in my club do that. A vector is always like that. Yeah, it's vertically like that. So when I write x transpose x, then that would look like that, and that's a scalar. Yeah, and if I were to write the other way, x transpose, then that would be this times that, and that's going to be a matrix. Yeah, I often find it easy to visualize these shapes than just stick to algebraic notation. Yeah, so that might be useful for you. And that's why this expression from the vector subtract the mean and then transpose off that is exactly the same, equivalent to squaring it. Yeah, and then the averaging gives you the covariance matrix. So that is kind of something you know. There was something else here that I wanted to say. This can go. You can see this by doing the lab, but I said to you that suppose I have some data, cross, 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 cross. Am I within the board, visible part of the board? Yeah. Okay, thanks. This one. So let's say x1 this way, x2 this way. And what I said to you here down here is if I were to take a direction, green is bad, let's throw it away. If I take a direction u, and this data is normal distributed. Oops, I'm going off the board, I think. Yeah. If the data is normal distributed with zero mean and covariance C, I've written zero because I happen to have drawn it as zero mean. Yeah, it doesn't have to be. And we said that if we were to project data onto this direction, can go here as well, then the variance of the projected data is U transpose CU. Yeah. If you went through lab 1, I'm setting up a scenario where you would calculate this variance, and then you will rotate this U over 360 degrees. And as you rotate, you will calculate this variance and you plot it. Okay. And I'll give you the answer before you do this. If you did that, you might find, say this angle is theta. Yeah. Now angle has become theta. Okay. That is criminal. I'm going to call it alpha. Okay. Let's call it alpha. And as a function of alpha, you can plot this variance. And what you will find is that it will look like that. Yeah. And the exercise for you is to explain why it looks like that. Yeah. And what do you get out of it? And I'm going to give you the answer because there is something very important underlying that. And you can easily see this is what would happen, right? Because you can see that if this U is aligned in this direction, the variance is very high. And if it is perpendicular that way, then the projected variance is very small. Yeah, this is pictorially correct, right? But you will work it out in code and also maths. Yeah, that's your job. Why is this useful? So if you look in this direction, the projected variance is largest. Yeah, so that looks like a special direction. Yeah, and because that is largest, I'm going to call this the principal. Yeah, and say it's a component analysis. So PCA is something you have come across here and there somewhere if you read the Guardian or whatever, we'll see PCA. Yeah. Why is that useful? That's primarily useful because we know data is largely distributed in that direction. And if we knew that direction, we might make sense of it. We might be able to use this. So imagine that it comes from data compression, really. So imagine you want to communicate this data to some faraway place. Yeah. And that data is described by an x1 and an x2, two coordinates. Yeah, x1 this way and x2 that way. So you want to communicate over this channel two numbers so that your friend at the other end knows where this data point actually was. Yeah, so you need x1 and x2. Now suppose the economy is not doing well and you're only allowed to transmit one number. Yeah, your channel is band limited. Yeah, and you can't afford a high bandwidth. You're only allowed to transmit one number. So, okay, the simple one solution would be to knock off x2 and just transmit x1. Yeah, so if you only transmit x1, you're only transmitting information in this direction, along that, and you're forgetting about x2. Yeah, there's a clever thing you could do if you asked to transmit only one number. And that clever thing is to observe that data is spread mostly in this way, compute this direction, call it U1, agree with the other party, U1 is the direction you're going to look at, yeah, and then transmit only one number along that length, along that direction. Yeah, so the distortion you achieve at the other end is minimum if you transmit along that number. Yeah, the distortion as measured by what is it that you need to communicate and what is it that you actually communicate. Yeah, if the distance is here and you communicate this one, you're making a bigger error than if you were to communicate distance along that one. Yeah, that's the basis of lots of data compression systems, even sitting inside your mobile phone. Yeah, we know that data is correlated, and that's why I've drawn these crosses this way. And you can compute and exploit that correlation so that the reconstruction error is minimized. Okay. So how would I do this without pictures? I might go and say, okay, I want to find U. That's the problem I'm trying to solve. And what should I achieve? I want to maximize U transpose C U, because that's the projected variance I want to maximize. Yeah, it's not an unconstrained maximization, because remember I told you I'm only interested in the direction. I'm not actually interested in the absolute value of U. Yeah, because if you arbitrarily tell me what U maximizes this, I would just say send it to infinity, put some really large numbers in U, and that would be very large. Yeah. So I need to constrain this in somehow. And because it's the direction is the only one I'm interested in, I would say subject to U transpose U equals 1. Yeah. Agree with that? So I'm solving here a constrained optimization problem. Yeah. And how do we solve constrained optimization problems? You know this from primary school. What you then do is you go and introduce what's known as a Lagrange variable. Yeah. And you write a function, Lagrangian, which consists of the thing that you want to maximize, yeah, plus some number times how much the constraint is not met. Yeah, this is a constraint that I want to achieve here. This is the function I want to maximize. So I construct this function. And then what I know from primary school is that the turning points of these would be places where I would achieve this objective and satisfy the constraints. So I go and differentiate that. I can't even write partial derivatives. Yeah. And when you differentiate that, you have 2cu take away 2 lambda u. Yeah. I'm writing this. If you're not familiar with writing these, then that Matrix Cookbook is an absolutely wonderful resource. Yeah, that's where you should go. You should also understand this derivative is differentiating this function. It's a scalar valued function with respect to a vector. Yeah, so differentiating, excuse me, differentiating a function with respect to a vector means differentiate that function with respect to each component of that vector, and the result is a vector. So this one actually contains partial derivative of L with respect to the first component, partial derivative of L with respect to the second component, and it becomes a vector. Okay, but in linear algebra vector notation, that's very easily achieved. So now, what can you do? Go back to primary school, you differentiate this, equate it to 0, yeah, and solve, right? So you equate it to 0, you push this onto the other side, then what you're also going to solve is C times U is lambda times U. Yeah, and that we know. Yeah, so this is telling you that what satisfies this are eigenvalues of eigenvectors of U, of C. Yeah, so what we have achieved is that these principal components that we are interested in PCA, yeah, are eigenvectors of the covariance matrix. So C is our covariance matrix. The eigenvectors of the covariance matrix tell you these principal directions. So the first one this way, and the second one this way. Yeah, so maxima and minima. And by looking at the eigenvalues, you can tell what they are. Okay, so we have looked at a property of multivariate Gaussians. Yeah, this is the one you were revising from the train. Yeah, remember? And we saw that you can use this property to sample. Oh, we haven't seen this, but I'll come to that. Yes, okay. We're going to use this property to sample from it. I'll get to that in a second. But you can also look at how projections, the projected data, what would it look like? And we know that the projected data will have large variations in some directions and very small in the others. And those are actually eigenvectors of the covariance matrix. Yeah, and you also know how to solve a constraint optimization problem to actually achieve that. Yes.
So is there any theoretical reason why that should be a straight line, or any kind of line should be working? The principle is that you want to make the variance the biggest when you project to that line, right? So one will whether that line can be a very different shape rather than a straight line. Is that possible?
Okay, so the question is, why should that be a straight line? This U1, why should that be a straight line? So the answer is we are only now working with multivariate Gaussian distributed data. Yeah, the idea of Gaussian distribution is the data is concentrated in some regions of the space, and it goes down according to the specification of the covariance matrix in all directions. In some directions it's large, in some directions it's small. That's the structure of the data we are dealing with, as coming from this equation. Yeah, remember this equation is what determines this, this, and that. Yeah, the property of this equation will give you these principles, these directions. Yeah, real data need not always be like this, and I think that's what you're alluding to. Real data can have multimodality. Yeah, there is a bunch of data here and a bunch of data there. In which case, this model, this density is not a good model of that. Yeah, real data in one dimension need not always be like that. You might have data like that, bimodal. Yeah. So our university thinks that exam grades of students should be like that. Yeah, they think there should be an average of something like 65, and there should be a standard deviation of something like 12. They drill this into me. Yeah, I go and set an exam paper and grade it, and it's more like that. Yeah. So I can't explain this to management of universities. I have tried, miserably failed. So, and there are reasons for this. If data is actually like this, you should not, what you should do is to actually go and ask why it's like that. Yeah, and there are very, very clear reasons of students' lives between school and university that lead to that kind of distribution, but we don't take that into account. Yeah, so even in very simple things, awareness of what's going on is important. So that's one. Data can be multimodal. The other is data can be highly nonlinear. Yeah, and we might be in a multidimensional space. Okay, so now I'm going to start sketching, and my sketching abilities are rather limited, so bear with me. So imagine, say, a three-dimensional space in which data sits in a two-dimensional manifold that, say, looks like that. So all your data is going to be here, 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 but it's sitting on a surface. Yeah, that surface is kind of looking like that, warped like that, sitting like that. It is still 2D. Yeah, it's not 3D. In a warped thing, it's sitting there. Yeah. So then PCA is going to be highly misleading. If you try to find which direction is the variance maximized, yeah, you will still get a direction. It's not going to tell you much. Yeah, because that is a three-dimensional space. Data is in 2D, but that 2D is a nonlinear manifold. Yeah, this is very, very common. And a lot of very recent neural net advances in machine learning or neural nets deals with this kind of problem. So we can build models that have a latent space of points. So now every point here corresponds to one point here. And then I'm going to ask the question, from 2D to 3D, I'm going to expand dimensions. Can I find a complex function that takes points in 3D and puts them on 3D? Yeah. Now this function is very complex. It's a deep neural net. It has 2 inputs and 3 outputs and loads of other things. Yeah. And because it has lots of nonlinearities in them, it is capable of projecting this kind of data into this kind of manifold. Yeah. And the idea of autoencoders and the probabilistic version of it is variation autoencoder is precisely this. Yeah. We said, go back to this one, principal components. We said along this direction, U1, yeah, which is the straight line you were talking about. If you project them, we maximize that variance. But we are going from 2D to 1D. Yeah, you're free to go from multiple dimensions to 2D. Yeah, so you might take data that comes in very high dimensions. So you might have data in 3 dimensions, say. Yeah, and you might apply a principal component projection onto 2 dimensions. Yeah, it'll give you a way of visualizing the data. Yeah, 3D, okay, we can visualize 3D, but maybe it could be 10D, and I can't draw 10 dimensions. Yeah, I'm not very good at this, but I might be able to project from 10 dimensions to 2 dimensions and study the distribution of data. Yeah, maybe some data are like that, and maybe there is some data here. But if in that 10-dimensional space, the distribution is along a manifold like that, yeah, then PCA would be highly misleading. Yeah, because it's maximizing variance. Its job is to preserve variance. Yeah, so there are various tricks in nonlinear ways of doing this. And one thing that's very highly popular is TSNE. Yeah, it stands for Stochastic Neighbor Embedding. Yeah, and with a T distribution underlying that. Yeah, you can look it up. Yeah, but what this does is to look at neighbors in this space and find a mapping onto a lower dimensional space in that neighborhood information is preserved. So guys who are neighbor here will also be neighbor here. Yes, that's what it starts with. And with respect to the probabilistic model, there are a little bit of tweaks around it. Okay, so it's a long answer to a short question, but I hope that's clear. Yeah, I might come back to variation autoencoders later tomorrow. Okay, so where did I start from? There's only one more thing I need to finish this part with, and that is we said sampling. If you go through lab 1 sheet, it has an exercise that tells you, if you tell me mean M, covariance C are parameters of a distribution, give me 1,000 numbers from this. The way I would do this is to first generate data that's isotropic like this, with 0 mean, unit variance. And this I can do just using the computer's internal functions. Yeah, the internal function that tells me np.random.rand n 100,2 will produce that for me. Yeah, because along each axis, I'm generating unit variance, 0 mean Gaussian. Yeah, and what comes along this axis has nothing to do with what comes along that axis. And if I fill this matrix 100/2 with rand n, I will get that distribution. What I can do then is to multiply this by some matrix. Yeah, because I know linear transforms will produce Gaussians. And because what I want is that distribution. That's what I want. Yeah, it has a mean here and a covariance matrix that you have given me, which has a correlation structure. This is what I can get out of the computer program. Yeah, so I get this and I ask myself, what should this transformation be so that I can go from here to here? But because I know it's linear transforms of Gaussians produce Gaussians, and you want 100 numbers according to this distribution, I would generate 100 numbers according to this distribution from my computer, multiply these by a matrix, and that matrix will produce this, and then shift it. That will produce this. Yeah, so the sheet in lab 1 helps you do that and learn that. Yeah, and what you multiply by is kind of like the square root of C. Remember I told you that if you ask me for Gaussian random numbers with variance 4, I would generate Gaussian random numbers from the computer with variance 1 and multiply each one by 2. Yeah, that's exactly what's going on here. I compute this one and multiply by a matrix that's equivalent to the square root of this one. I need to be careful with the language there, which produces that. And that comes by what's known as Cholesky decomposition of C. So if you write A equals Chol C, that's a factorization of C that gives you something like square root. Okay, so that's in the lab sheet you can go through. Okay, so that's quite a lot to take in. Let's push this down. Now that we know some of the things we are going to derive, let's go back to, so now we can run through this very fast because it's the concepts that are important. The algebra can be worked out as long as you have a pencil and a piece of paper. Okay. So what do we have here? We are going to assume that there is some group of data. This omega j for me is some label on things. Yeah. Parameterized by theta, that's the distribution that we are of interest. When we study classification, you will understand why I'm using this notation. And the distribution is Gaussian, mean at J, C at J. Okay. Oops. Okay. So you are giving me data x1 up to xn, and this data has been drawn from this probability density. That's the story. Okay. There is this concept of identical and independently distributed IID samples. That's a very important statistical concept. You have an underlying data generating source, and you have drawn some data from that, and you have to do that always from that distribution that's identical. You have to be independently draw so that you don't look at what you have drawn before in order to draw the next one. Yeah, this is an extremely important property, so that many of these will work. You'll see that in a second. Yeah. So all samples were drawn from this distribution. They are independent draws, and the previous value doesn't affect the next draw. And then comes the idea of a likelihood. The idea of a likelihood is a function, yeah, of how much what you get when you have this data parameterized by those parameters theta. Yeah. So what you're going to do is, given into that functional form, which is normal distribution, you're going to plug in the data that you saw, the value that you actually have, to get this likelihood. And that likelihood is a function of the unknowns. Yeah, that you have to be very clear in your mind. You have a mathematical expression in terms of x and m and c. Are you with me? X is the variable, m is the mean, c is the covariance. Yeah, you have that. Now, in the space of x, this function takes a particular form. If you give me m and c, what I'm going to do now is, I have data which are the x's. I'm going to ask, what's the best value of m and c that will fit this data? That's the problem I'm trying to solve now. Okay, so the likelihood is going to be a function of the m and the c. And this likelihood for an individual item of data would be just plug in x of k that you have observed into the formula that's somewhere on this board. Yeah. But once you have n data, yeah, a lot of them, 100 of them, then the likelihood of the entire data set that you have observed is a product of the likelihoods of individual data. Yeah. What enables me to write this as a product? It is the idea that I have drawn them independently. Yeah, that's why this independence is important. So if the events are independent, then the joint probability is the product of all those probabilities. That's where it's coming from. Okay. Oops, I'm making this mistake again. Okay. But often it's not a good idea to work with likelihoods. Algebraically, that's not a good idea. Why? Because often we encounter e to the power something. Yeah. So when you have e to the power something, if you take log of it, then the exponent disappears. Yeah. We have products of things. I've written a product here. If you take the log of it, it becomes sum. Yeah. So when you lose the exponent and you turn the product into a sum, life becomes much, much easier. Yeah. But you won't lose anything. The reason you won't lose anything is logarithm is a monotonic function. And where a function becomes maximum is exactly where it will become maximum if you take log of the whole thing. Yeah, that makes life easy for us. So we almost always work with log likelihoods and not just with the likelihoods. So what we do, like we go back to primary school, we write the log likelihood and we ask the question, what theta hat maximizes, what theta maximizes this? And that's the whole idea of maximum likelihood estimation. Yeah, you have a generative model, you have observed data, that model has parameters, you plug in the data into the equation of the model, you get a likelihood, take the log and maximize this. Okay. And like I've said already, so maximizing by taking the derivative and setting it equal to 0. And this is what we always do, right? From primary school, you differentiate something, equate it to 0, solve for the unknowns, you get an answer. Yeah. So here's an example. So the example is multivariate Gaussian, like we have down here. And let's assume that the mean is not known, but some genie has told us what the covariance matrix is. Yeah. So I'm sorry that my C has now turned into sigma someplace. No, it's still C. Okay, good. Okay. So what do? We know the equation down here. we plug in the observed value xk, yeah, and take the log of it. The exponent has disappeared, so you have this term that was on top of the exponent here, and we have the log of 2 to the d, 2 pi to the d, and determinant of c. Yeah. Differentiate this, and if you go and differentiate this after looking at the Matrix Cookbook relationships, yeah, it's very, very similar to if you differentiate x squared, what do you get? 2 times x. Yeah, it's very similar to that, but because this is not dependent on m, on the mean, it won't contribute anything. Over here, I will have a 2 that's coming and canceling the half, and I will have c inverse times x minus xk minus n. Yeah, so this would be the derivative. But remember, I have just written this for one data point x of k. If I had n data points that you give me, then it will be a sum over all these n terms. Yeah.
Here we've assumed that the likelihood is a Gaussian, right?
Here, yeah. So the question is, have we assumed that the likelihood is a Gaussian? If we are more precise with terminology, with language, then we'll say the underlying model is Gaussian, which has parameters m and c. That's the assumption. And you have given me data, which is xk, and you're asking me what's m. C is something you assume you know in this setting. Yeah.
So how do we choose how the model is the likelihood is based on the
That's where the model you are fitting comes in. So Gaussian, and what are the best parameters of the Gaussian are the simplest in which I can tell a story about the difference between Bayesian estimation and frequencies estimation, which is what my job now is. Yeah. But the likelihood you would write is based on what the underlying probabilistic model is that you're working with. You might be solving a population genetics problem, and you might be working with discrete probability models. You might be solving a queuing theory problem, and you might be working with Poisson distributions and point processes. Yeah. So depending on the problem you're trying to solve, there will be some underlying probabilistic model that you have to recognize. You have to recognize what their parameters are, and then write out the likelihood. And then comes even more complex parts of life where you cannot explicitly write down this as a formula. Yeah, those are the non-parametric worlds of statistics. Yeah, life becomes even more complex there. Yeah, so I'm making my life easy by working with the simple ones and pushing you into the deep end to solve the bigger ones. Yeah, good. So, okay, so when you do this and solve this, then what you get is your estimate. I'm sorry, that's gone below this. Estimate of the mean is the average of all the data. Yeah, it's a very simple result that if you give me some data and ask what's the mean, you add them up and divide by how many data you had. Yeah, but the underlying principle from where it appears is the maximum likelihood framework. You had the assumption that it's a Gaussian distribution from which it's coming. You wrote down the formula for it. You substituted the data to get the likelihood. You wrote it in, you took the logarithm so that you lost the product and turned it into a sum. You lost the exponent. Then you differentiate it, equate to 0. You get the result that you need from childhood. Yeah. Okay. Take another example. It's univariate Gaussian this time to make it easy, and say the mean and variances are unknown. Yeah. And in the example that I took, it's reparameterized. So they take as parameter 1 the mean, and the parameter 2 the variance. Yeah. So differentiating with respect to this variance is easier than the sigma itself. And I think I'm going to skip past this because here there are 2 things unknown. And where you would end up with is 2 equations, simultaneous equations in θ1 and θ2, and your job is to solve them. Yeah, you can go through that at your leisure and manipulate a bit of algebra, and you get estimates of the mean and the variance. Yeah, and these are equations that you already know. These are programmed into your pocket calculator. And the question I was asking is, why is it that there's a sigma n and sigma n minus 1 in the calculator? Yeah. Okay. Similarly, results for multivariate Gaussian, we can skip past that, and we get to the idea of Bayesian estimation. Okay. What happens here? There is some data like before. So there's a likelihood that we can compute as before with a probabilistic model. But I also have some prior uncertainty over the parameters. So I come into the room thinking that there is a prior distribution over the mean, which for convenience, let me say, is also Gaussian, but it has a mean at M0 and variance sigma naught squared. Yeah, this is what I came in to teach here with having taught somewhere else, where the students were scoring on average 60 marks with a standard deviation of 10. Yeah, these are the numbers that you guys are scoring. They're in the range 78, 80, 85, and so on. Yeah, I want to calculate the average. Yeah, so I use Bayes formula to this, and that's why the term is called Bayesian here. And Bayes formula tells me the probability distribution over the mean conditioned on all the data, this is the way to read this, is given by, this is the probability distribution of the data given M, so that is a likelihood term, multiplied by the prior probability of M, P of M is what I came into the room with, and a normalizing constant below. Yeah, to make the left-hander probability, this equation should be that the denominator here is an integral over all the possibilities of the numerator. Yeah, you with me on that? Yeah. So what we would do, because the denominator is a constant, we can forget about it for the moment, just take it as alpha. Yeah, so 1 over alpha is that constant, and work only with the numerator. And the numerator has the likelihood as before, which is obtained by plugging in the data, and the prior that sits next to it, which is multiplying it all the time. Yeah. And this is the posterior distribution. It's known as a posterior distribution. Why is it known as posterior? It is your uncertainty on the mean after you saw the data. The prior is your uncertainty on the mean before you saw any data. Sorry, not that. That's the prior. Yeah. So the idea of a prior is what I brought into the room. The idea of likelihood, which is what I observed in the data in this room, the combination of these two is going to give me the posterior. And that combination is happening by Bayes formula. That's the only secret. Yeah. That's the idea to understand. The rest is technical, and that technical part is difficult, but that's what it is. Yeah. But there are tools out there to help us do that. So once you have this, there again is a tiny detail, important detail, that one of the things we often do is maximize this posterior distribution and get one set of values for the parameters. An alternate way is to work with that distribution entirely. And then, like I said right at the beginning, integrate out all the unknowns to make an inference. There are two ways of doing this, but let's ignore that for the moment. Okay. So here's a simple example, univariate Gaussian. So if you have gone to rest, wake up now. This example leads to something interesting you can observe. So what do? We only have the mean is unknown. So I want to understand what's an average grade this class gets in machine learning. Yeah, I have come here with a prior, and I have observed your results. My prior is Gaussian 60 plus or minus some standard deviation. What I observe in the data here is 80 plus or minus standard deviation. I'm going to combine the two. Yeah, and that's the story here. And the story you can see will involve a Gaussian term, which is based on the data that you observe, and a Gaussian term that's based on the prior I came with. Yeah, is there a question there? No, okay. Yeah, so two Gaussians, both have 1 over root 2 pi type terms, normalizing terms, e to the power something terms. Yeah, one is coming from the prior that I came in with. Yeah, what is the distribution over the mean? Is the mean minus the 60 that I had and the plus or minus 10 I had. What do I get from the data? I have to sum over all the data that I have, subtract the mean, square it, divide by the standard deviation, and what I get. Yeah. So what you have to do is to go through this manipulation of this, and Bishop's book does this beautifully. This Gaussian product is also Gaussian. Yeah, and he uses that result very elegantly into this, and let's do that. And let's go to finally what happens. Sorry. This is what we have finally. What we have is that the posterior mean that we have is dependent on two things. One is the prior mean I came with, and the mean I estimated through maximum likelihood. Okay. If I came to the room without any prior knowledge, yeah, I'm just a normal frequentist statistician, then the first term is this m hat n is the only thing I have. But I come here with a highly prejudiced form of views. Yeah, so I'm a politician, I'm not going to change my views. That's m naught. That's what I came in with. Yeah. So the true mean that you're going to estimate now by maximizing the posterior is going to be a compromise or a balance between what I came into the room with and what the data is telling me. Yeah. If I stuck to the data alone, I will grab all your marks and average them. Yeah. If I didn't see any of you and I had my prior prejudices alone, then I'll tell the boss the average mark is 60. Yeah. But now that I have my prior knowledge plus observing you guys, I'm going to balance the two. And that's what this formula is doing to me. Okay. What's my posterior variance? That's going to be dependent on the prior variance that I came into the room with and what I measure from the data, a formula that pops out like this. Let's put some sanity checks on this. Yeah, does this actually work? Suppose I am a very dogmatic person. Yeah, I actually am, but yeah, almost religious. I'm just going to say it's 60. I'm bloody certain it's going to be 60. Yeah. What that means is my sigma naught, that my prior variance would be tiny. Yeah, I'll say 60 plus or minus 0.01. Yeah. So if this is very, very small, the sigma naught is very, very small, then you can ignore this with respect to the sigma squared. You can throw this out. This ratio is 1. Yeah. Over here, sigma naught is very, very small. So the numerator is 0, negligible. Yeah. So anything I saw from you guys, however well you did your exam, I'm going to ignore you completely, right? Because my prior is very, very strong. Yeah, so that matches this. Agree? What happens if instead of 80 of you, there are 800 of you? Yeah, I mean, machine learning classes are very popular. We get huge numbers of students studying machine learning. Our first machine learning module we teach now is about 320 students. Yeah. So n is very large. The sample size is very large. Yeah. If the sample size is very large, this term here is much larger than sigma squared. Yeah. So the denominator dominates. Yeah. So this term becomes 0. Yeah. So the prior mean I came into the room with has no effect. Yeah. So there's such a large crowd here that it's your marks that give me the ultimate answer. And the prior I came to it has been swamped by having loads of evidence. Yeah. So I'll leave you to think a little bit more about it. Is there anything else that you can say about posterior uncertainty, prior uncertainty, and so on? But you can interpret this. And that is one important aspect of this subject of machine learning. That you are able to think of something, you are able to derive some results from that, and you should ask if there is sanity checks you can do to ask whether they make sense. Okay. So I think that point I'll stop with estimation. There is not a lot. I've written down what I've said here. That is not me. I think that's okay. Yeah, that's fine. Okay, so let's now do this. And how much time do we have, Sami? 10 minutes, okay. So I can introduce you to the next problem. So we have looked at an overview of machine learning. We have looked at estimation as an idea. And we have looked at some basic tools to do with probability densities. Yeah. So what I'll now do is to switch this off and go back to the board. And I'm going to introduce you to the problem of classification. Yes, I'm going to do that in a minute. I take this one. Oops. Oh, stop share. So I'm going to use a lot of what I already talked about with these densities. And the problem I'm going to tell you about is monitoring my machine learning class. Yeah, and being, we teach machine learning and then we have to assess students, give them exams and grade them and so on. So being a lazy person, I don't really want to do this because I will do this every year, year on year. If I can do some predictions, it'll be nice, right? Because at the end of the day, what we want is those students who pass machine learning and those students who are trying to pass machine learning, right? The two types. So what I have done is I've stuck some cameras all over the place, and I'm going to measure the time students spend in the library and the time the students spend in the bar. Yeah. So what would we find? We'll find I have students here. So I observe lots of students here. Do you agree that might look a little bit like that? Negatively correlated because there is finite time people have. Yeah. And there are many students who are the red students. So the red students are trying to pass the subject, yeah, because they seem to be spending an enormous amount of time here, yeah. And the students in black are doing okay in the class, yeah. So now all I have to do is student comes into the next year's class. I just observe where they are, yeah, and I can decide whether they pass or not, yeah. So it's simple now, right? I can't give them a continuous grade, but I can compute the probability that they will pass, and then that could be a continuous grade there. So a couple of things come in here now. One is the student spending time here and here. I can say it's a vector, it's a feature vector, time library, time bar. That's going to be a vector. Yeah. There are two classes of students. Class 1 are the black crosses, and class 2 are the red crosses. Yeah. A priori, from last year's experience and what my rest of the population tells me, they might tell me there is a probability of class 1 is 0.8. 80% of the students pass machine learning. This is what has happened last year, the year before. Yeah. And the probability of students failing is 1 minus probability of C1. That's also reasonable. Yeah. In this one, my cameras have not been used. That's important. Yeah. So I have not used my cameras here. I've only asked the tutor of last year. Yeah. So this is some kind of a prior. Yeah. By sticking these cameras in, I have made an experiment. Yeah. I have collected data of where they are, how much time they're spending where. Yeah. The way I have drawn it, it looks kind of Gaussian. Yeah. So I can fit a Gaussian model through this. I know how to do this because we have just done estimation. Yeah. And that's going to be the probability density of X given class 1. Are you happy with that notation? I can take all the guys who did not pass machine learning, or who are trying to pass machine learning, yeah, fit a distribution. And then I have the probability distribution of the variable conditioned on those people who did not pass. With me? Yeah. So what I now have are priors here, and those ones I can call likelihood. Yeah.
Are they from the same class? C1, C1.
Are they from the same
class?
Same class? No. So, okay. That's a very good question. The question is, are they from the same class? So in my language, the class is in classification, different groups, yeah, different targets. So it so happens that the term class has come with that. So yes, you see the confusion there, right? Good one. So what do I want to now do? So the tutor tells me 0.8, 0.2 from previous year. That's a prior. My experiment gives me these two. So I'm going to do exactly what I just said, Bayesian idea of combining the two. Yeah. So I might now go and write the probability of something I would be interested in, really interested in, is the probability someone would pass conditioned on a measurement. Yeah. So I go into next year. A student turns up. I have been monitoring this student in the library bar time space. Yeah. And I have got some measurement. Conditioned on that measurement, what's the probability the student will pass? That's what I'm interested in. And that's a posterior. Why is it posterior? It's posterior because it happens after I have observed the student. Why is this called prior? It is a probability before I have done any experiment. Yeah. These likelihoods are the ones that I have gathered as a result of doing the experiment. Yeah. Those terms should be very clear in your mind. With me? So once you have that, then I can go back to Bayes formula. Bayes tells me how to handle this. Bayes tells me the probability of C1 conditioned on X is going to be probability of X conditioned on C1, probability of C1 divided by the normalizing constant is called probability of X because I've integrated out C1 to get that. Okay? There's something important about this one. This is going to be P of X is going to be probability of X given C1 times probability of C1 plus probability of X given C2 times probability of C2. Yeah, the denominator is computed by all the possibilities summing together because otherwise this will not be properly normalized as a probability. Because once you have observed X, you only have two things. You have probability of pass given the data and probability of not pass given the data. Yeah. And they should both sum to 1. With me? Because this student who has been observed spending so much time in the bar and so much time in the library can either pass or fail. There can't be anything else. Yeah. In that case, those two should add to 1. And in order to enable that, this denominator has to be that form. Okay. So what we will, any questions there at this point? Are there any questions on the chat? Say it again.
There was one student class call saying what is the latent space.
Okay, yeah. So the question was, what is the latent space? Latent means hidden. That's what it means. Yeah. So if you say I'm observing data in 3-dimensional space, but that data is driven by a 1-dimensional mechanism that is hidden from me, I'm calling that a latent space. Yeah. You had a question?
Yeah. So in the case of when you're trying to predict of a certain student,
yeah,
for example, whether they fall into C1 or C2, would there have to be like a certain parameter, like a cutoff point, whether they be classified as C1 or C2? So like in the part where the
right.
Are like,
okay, good question. Good question. The question is, would I always classify someone as passing or failing? Or is there something else I can say in the region where these two data overlap, for example? Yes, absolutely. So what I have now done is I have collected data from those students who passed. I have collected data from those students who failed. And I have computed the likelihoods of both those. I have computed probabilistic models of both those. I have some prior with which what I can compute is a posterior probability. Yeah, that's this P of C1 given X. This is the probability a student would pass. So I can jolly well say, if this is bigger than 0.5, I'm going to pass the student. Yeah. Alternatively, I can have a reject option and say, I'm not going to call a pass unless this is about 0.7 or something. Yeah. Close to the boundary, I may not make a decision. Yeah. In other issues, other context, this could become even more interesting in the sense that you might define for me a loss function associated with misclassification errors. You might say, if you pass a student who is supposed to fail, then my salary will go down. Yeah, in which case I will set the threshold accordingly so that I don't make that mistake. Yeah, so I can either have the boundary here, which is at 0.5, yeah, or if I am penalized for passing these guys, yeah, I might push the boundary there. Yeah, and that's up to me. So what this framework is going to give me, this base formula is going to give me, is a way of calculating the posterior probability. And that posterior probability absorbs any prior knowledge I had and what I have modeled through doing the experiment. Yeah. The next step of cutting a threshold can be dependent on other things. Okay. That's where another interesting thing happens. That is, if you set it at 0.5 and classify above 0.5 pass, below 0.5 fail, I will minimize the error rate, the number of errors I make. Yeah? But I can make two types of performances here. I can talk about two types of performances. I can say these red crosses to the other side of this boundary. Suppose I set the boundary here. Yeah. The black crosses to this side of the boundary is one type of error. That is students who should actually pass, but I'm failing them. Yeah. The red crosses to the other side of the boundary are students who ought to fail, but I'm passing them. Yeah. So you can talk about false positive. That's the guys who should fail, who have been passed. And what fraction of those who should pass I have passed as a true positive. Yeah. So in quantifying performances of classifiers, these are very important. Yeah. So what would I do? I will have some threshold on this continuous value, on this probability, and I can call, depending on where I set the threshold, strike a balance between true positives and false positives. Yeah. So I think that's a good place to end by showing you a small whatever. And what I'm going to do this is a small graph. So what I have here, let's do that. Yeah. So suppose the red line here is a probability distribution of the students who pass. Yeah. And the green line here, green is a distribution of students who don't pass. Okay. Or a medical context is much nicer. You go into a hospital, you do some tests and produce a score from that test. And the red ones is the distribution of people with a disease. They're scoring high on that. And the green one is the people who don't have that disease. Yeah. And I have summarized those multiple measurements into one score Y, which is what the medical textbook tells me. And this is what I have. Yeah. So now what I can do, I can cut a threshold somewhere here and say that anything to the right of that threshold, I'm going to call sick. Anything to the left of the threshold, I'm going to say fine, go away. Yeah, that's how I would classify based on a continuous value, cut a threshold and say above this, you are sick, below this, you're okay. Yeah. So two types of errors will come about, or two types of performance will come about. If I cut a threshold somewhere here, then the area of the red curve to the right of that threshold is my true positive. Area of the curve, area under the curve to the right of the threshold is the fraction of people I would get as correct from the red population. The area under the green curve to the right of the threshold are my false positives. Okay? Because those are the people who are green, but I'm going to call them red. Agree? So as I change this threshold along the y-axis, I can get different operating points in a true positive, false positive world. Yeah? And what do they do? Oops. Yeah, as I move the threshold, I get different operating points. It took me a lot of time to draw this, so you should watch this again. How do I do this? Go back. No, it doesn't seem to. Oh, that's really sad. I got it. Yeah. See, that's nice. Okay. So you can see that as I allow more and more false positives, I can get better and better true positives. Yeah, but I cannot do both at the same time. Yeah, and this curve determines that. And what you can immediately also say, a couple of things. One is this curve is called the ROC curve, Receiver Operating Characteristics curve. And the area under this is of interest. Why? If I had this red and the green far apart, yeah, then I have a good test for illness. My hospital is very good. Yeah, and this ROC curve will go up there and be like that. Yeah. If I have a really bad hospital, yeah, and the tests are really bad and nothing to do with the illness in a way, they're going to measure shoe size and predict something wrong with you. Yeah. Then the green and the red will overlap on top of each other. That's the extreme case, in which case this operating point would be on the 45-degree line. Yeah. So it's good to have a big fat ROC curve. Yeah. And that's a good thing to do, but that has a very nice statistical interpretation, and then that's important. Okay. So one thing some of you might already know is that the area under the curve is used as a performance measure. Yeah, because it strikes a balance between true positives and false positives, and people like this. This is better than accuracy. Why is it better than accuracy? In the health context, for example, 99% of the population hasn't got an illness, thankfully. 1% has an illness. Yeah, so your prior is very high on the not having illness. Yeah, so now you don't need to do anything to have high accuracy, right? To get 99% accuracy, all you have to say is everybody's healthy. Yeah, then you only make mistakes on the 1%. Yeah, so you have to have this balance between very large dominant one class and a tiny other class, and this is what achieves that. Okay, so the area under the curve should be very high, and that's used as a performance measure in comparing classifiers, but it has this neat statistical interpretation. Look at this. Suppose you give me two people, send two people into the hospital, and you know one person has an adverse outcome, this person is sick, and one person is clean, they're healthy. Yeah, and then you ask me to rank them. Yeah, so you send me two people and ask me to rank them. And then you send me two people again, ask me to rank them. But you know one of them is healthy, the other is not. Yeah. The probability I will rank them correctly is the area under the ROC curve. If I just randomly say this one is healthy, this one is healthy every time you do a test, then I'm behaving at random, and my performance would be on the 45-degree line, and it's half. Yeah, I don't rank them correctly on your tests. Yeah. If I have a good ranker, if I'm well separated, yeah, then I'll always put the sick person as high chance of being sick, and my area would be 1, under the curve would be 1. Okay, so that's a very, very useful measure, but there is a lot more to it than this. I only touched on true positives and false positives because that falls on this graph, but there are many other. There are two others immediately, true negatives and false negatives. You can think about that. Yeah. And there are also in the information theory, information retrieval literature, precision and recall as performance criteria. So this literature is quite good and very rich. And the nice place to read about it is the Wikipedia entry. So if you do ROC curve and hit the Wikipedia entry, that entry is quite very nicely written. So you can read quite a lot about this, what the assumptions are, where they're coming from, and so on. So we don't stay with accuracy just to finish with, we stay with the ROC curve and its area. But this also suffers sharp criticisms. Because when you think area under the curve is your performance measure, what you're saying is you are integrating over all the false positive rates. This is not realistic. Yeah? You're not interested in designing a system and installing it and thinking about all the possible false positive rates. You will have some idea what is a reasonable range to operate in. Yeah? So in any practical application, you would not just deal with this, but to publish papers comparing algorithms. This is what we do. That critical review and that literature is from David Hand, a very leading statistician in this country. So I think I'm going to, before I stop should I say something about what we'll do tomorrow morning? No, tomorrow morning we'll continue from these passing and failing students and derive some simple classifiers, what are the underlying things are, and then ask why we should build neural nets as stronger ones, and then we'll ask why we should build deeper neural nets after that. Okay.